Plate tectonics is the scientific theory that explains the movement of continents over the Earth's mantle. The driving force of a continental drift is natural heat convection within the Earth's mantle. Because of heat generation from the Earth's core, mantle convection is responsible for all major geological developments, including the creation of Pangaea. Plate tectonics is also the driving force behind the formation of mountain ranges, volcanoes, and seafloor spreading. The phenomenon of plate tectonics is driven by natural heat convection, in which fluid motion is induced through heat transfer from the Earth's core to the adjacent mantle. The solid silicate mantle can essentially be treated as an extremely viscous fluid. When the transfer occurs, the fluid density decreases such that it possesses a greater buoyant force to trigger upward motion through the fluid above. As a result, buoyancy enables circulation in which heated fluid rises and displaces the surrounding material. However, during this rise, the fluid is continuously subjected to energy transfer with its surroundings, causing its temperature to decrease. As it approaches the relatively cool surface above, its density gradually decreases until it begins to move back down towards the heat source, completing the circulation. This cycle occurs in several cells distributed across the body of the fluid. The separation of the surface above the fluid occurs because the convection currents at the top of each cell move in opposite directions. This serves as a driver for the surface to split.
Natural convection in the mantle can be experimentally modeled using a milk and cocoa system. The rationale behind this setup is simple. If a heat source is placed under the milk, heat transfer will enable natural convection in the milk body. The milk adjacent to the heat source should acquire a lower density, causing it to displace the more dense milk above it. A heat circulation pattern similar to that seen in the mantle can be expected. If a layer of cocoa is placed above the milk, the opposing convection currents near the upper milk surface should cause the cocoa to split. But how appropriate is this model? Well, Rayleigh number is used as a numerical metric to describe natural convection, with larger values indicating more turbulent heat flow and greater heat transfer. For enclosures, there's a critical value of about 1000, over which we can expect natural convection to dominate heat transfer by conduction. The Earth's mantle has a Rayleigh number of approximately 10 to the 6th to 10 to the 8th, while that of our milk-cocoa system is approximately 10 to the 10th. This provides evidence of natural convection in both cases, making the milk-cocoa system a suitable model for the Earth's mantle. However, we should expect splitting of the cocoa to initiate and proceed at a rate far greater than that of the crust because of several reasons. First, the cocoa layer is less dense and less thick than that of the crust, and secondly, the Rayleigh number is greater, indicating a higher rate of heat circulation due to natural convection.
Chemical engineers can develop models based on fundamental heat transfer principles that can expand our understanding of the dynamic underlying plate tectonic theory. Equations, including the Rayleigh number, provide the foundation for more complex models that explain these phenomena.
To begin the experiment, we first gather the required materials: milk, cocoa powder, a metal container, and a heating plate. Place the container on the heating plate held at a maximum temperature. Fill 1/4 of the container with room temperature milk. Then completely cover the milk surface with 0.5 centimeters of cocoa powder. Observe the system until the cocoa surface begins to split.
Prior to heating, there is no heat convection, and therefore no perceivable cracks in the cocoa surface. After 10 minutes, there is enough heat transfer to trigger convection in the milk, which causes initial surface splitting. After another 2 minutes, the cracks propagate throughout the surface, allowing for individual surface plates to form. Finally, the milk overwhelms the surface, which recedes back into the medium.